All right, I see the timer has already started, so let's begin. A quick introduction. I am Mrityunjay Gautam. Most of my friends here call me MJ. You can do that. I'm the Senior Director of Product Security at Databricks. And in the past, I have approximately 16, 17 years of experience in security. I have played on both offensive and defensive sides. And I've had the opportunity to run SDLC teams for over a decade now. Red teams, incident response, practically. Most of the things which requires security and code. You combine those two things, I've played with it. My co-speaker, Pavan, was not able to join, health emergency, so hopefully he would be happy when he sees the talk. Before I begin, I would like to make a quick disclaimer. None of the views here are related to Databricks, so if you have to sue someone, please don't sue Databricks. Thank you. Let's touch the problem statement a little bit. So there were very good days when there used to be features which were in the waterfall model going on for months and quarters, sometimes 6 months, right? A lot of good time for security teams to be able to go through all the security reviews, which is great, right? And then came Agile, and then became cloud, and we went into the two-week sprint models. So what happened in the process was that the speed of development went up crazy high. I'm more than sure everybody here knows that. The other reality is that the ratio of security engineers who are actually reviewing the code and the design compared to the people who are actually creating the code and the design is something, on a good day, it's like 1:100. On a bad day, it could go to 1:500, right? It could be anything, right? So what we started doing as a security community was like, hey, you know what? Let's ask our friends in the development team, can you help support making those decisions for us that which feature you're working on would require a security review, bring it to us, we'll help you out. We also wanted to, we started with champions program, security advocates. They're called different things in different companies. But at the end of the day, that was sort of a hack. The reality is that a bunch of features did get reported to security. And we as team, we work on those things. We do our best to secure it. Great. But the reality hits there. What happens is that the people who are making the decision whether something is required for security or not versus the people who are actually experts in security are very different. So there's a significant blind spot there. There are a whole set of things which get released without even realizing that this requires a security review. When do we get to know as a security team? Hold on, there was an incident, right? And something got hit. And we are saying, when did this API release? How did it become public, right? We didn't know about it. Oh, because the developer thought it's just a small change, no big deal, really. It was a big deal, okay? So I'm more than sure a lot of you would have seen that problem. I have seen it multiple times. So the obvious problem which we wanted to explore was that how can we consider the security review decision-making as an automation problem? Now, just to touch a little bit about it, what is really an automation problem? So typically, an automation problem is something which is repetitive, high volume data, process oriented, something which is you want to constrain in time, but it does not require too much of a human intelligence. You can just code it through, goes through. That's what automation has been till date. The small problem here is that if you have to make a decision whether this requires a security review or not, it requires domain expertise on security. It requires you to have at least a minimum bar on intelligence. And it does require you to have some domain knowledge on the product itself, right? Because things mean different in different worlds. So the hypothesis which we started with, which I want to explore here, is can we solve this basic bar of intelligence using a bit of a natural language processing and deep learning, right? And can that help us automate this whole process in something which is more credible? What I'm going to do is, for the rest of the talk, the example I'm going to play with is Apache Spark. This is an open source product out there in Apache Software Foundation. And the good part is they have all their features listed in a public Jira. So you can actually open the ASF's Jira and you can see all the features. It's not just Apache Spark, but practically every Apache product is listed on that one. So we'll take our examples from here. throughout the talk, and we will discuss how it goes. But before we go there, one of the critical things that we have to realize is that when we as engineering professionals or security professionals, when we talk in our workspace, that's, let's say, and assuming you're talking in English, then the language you're using is not exactly the spoken English that you would speak outside the environment when you're talking to your mom, for example, right? Assuming your mom talks in English, right? So a lot of assumptions here. So this is something which I think first time that hit me was, I think, my third year of college when I was doing the OS course. And it was interesting because the first word I saw was cow, copy and write. I was like, dude, this is cow? Okay, that's funny, interesting. Is that the only example? If this was one example, we could have probably just, hard-coded it, solved the problem, but that's probably not the case, right? Who here understands POC as a proof of concept, right? But you know what? It does also mean people of color. If you go out and you start talking about it, right, with non-security, non-engineering people, that's what they understand when you say POC. Great. And Spark, come on, I'm using Spark as an example, so it does warrant a mention over there. And Spark can mean Apache Spark to a lot of us. It could also mean electric spark, a spark of fire, or a spark between two people, for heaven's sake. All right? It could mean a lot of things. So the point I'm trying to make here is that the spoken English versus the engineering English is very different. And if we are trying to use natural language processing to make sense out of a document, to make a predictive decision, we need to understand this language which engineering uses. So let's start with some super high-level basics on machine learning before we dive deeper into this. So a couple of ideas that we're going to use is, stage one is a classifier. A classifier is at a very high level. Supervised learning is used for classifiers when you have a labeled input. You already know that here is the input data and this is the class it belongs in. You train a system and it kind of classifies it. Again, you can see there are some different colored dots in different sections. What I wanted to clarify is that no matter how good your machine learning system is, if you're getting 100% accuracy, there's a problem. So you have wrong data over there, right? So there's always going to be situations like that. One of the things that I'll be using in this discussion is a multi-layer perceptron. So this is a basic artificial neural network, which is essentially a mathematical representation of your brain neurons. It's a universal classifier, and that's what we try to use in the, in the code. So this actually takes numeric inputs and it gives you numeric outputs. So we need to have some way to represent words as numbers, and we'll try and see what all things we can do over there. So the first step to solving any machine learning problem is collecting a training data, right? Without data, there is no point in doing any kind of learning. You just can't do it. So let's start there. What are the good sources of data around engineering text or security text or anything, right? I'm more than sure everyone here would at least relate to a few of these symbols out there, right? There are like, you could use, the Microsoft Office series or a Google Docs or Jira, AHA, Confluence, whatnot, right? Bunch of things, most of us use it. This is where all our design documents, your PRDs, your security bugs, your bug bounty reports, your crash reports, all sorts of things are listed out there. This is a very good collection of data in terms of what documents would look like when you're talking about an engineering problem. And honestly, I don't want to go into each of this, but those are pretty standard strategies by which you can extract the data, you can start processing it, and you have to create the corpus. So you could use PAT tokens for Jira, Confluence, OAuth tokens, API keys. Sometimes it doesn't even require authentication if you're picking up public documentation and stuff. Now the interesting part is what kind of data corresponds to requiring security review versus not requiring security review. And remember, the point is not here to actually mark things explicitly that, hey, this feature requires security review, you should keep it. No. The idea here is to understand the language which is going to be used, which associates the document to requiring security review. So the labeling here is not necessarily as stringent as anything else. So a very good set of examples are security defects, bug bounty reports, feature documents, stuff like that, right? Some feature documents do require, some don't, right? So it's something you can kind of get together. There are class of documents and features like your machine learning documents or ops or non-security escalations, stuff like that, right? Which we know for sure don't require security reviews. We can kind of classify them together. So this is what we're going to use as a positive and negative data set. So first attempt, okay? As you know, first attempt always is not successful. So let's talk through the journey. Our first attempt to build this model, we'll call it the model version 1.0. Didn't decide to give it a name because it's not successful. So let's start there. So the first stage was to build a vocabulary. So now that we have extracted the content, as we were talking about, the first thing you do whenever you're dealing with the natural language is you go through a text cleanup, right? There are multiple things you can do there. You need to remove the numbers, remove single letter characters. You can remove something called stop words. Stop words are a very interesting concept. There are dictionaries of stop words available for each language. So for English, those are like articles, prepositions, which really do not mean much in the world of decision making for security, right? So if I remove a and the of it, right, doesn't really matter. It's out. So those are stop words. And then you don't want to have lowercase and uppercase dealing differently. Doesn't make sense, right, from a decision-making perspective. And finally, you need to create a vocabulary. So let's take an example of this. So what I did was, this example actually picks up one of the Spark tickets from the ASR Jira, right? And that's what the text looks like. So if I take it the first step, you tokenize this using NLTK. So when you tokenize it, you're basically parsing it out based on the white spaces. So that's the tokens. You remove all the 2 characters and numbers and everything, right, which is great. So all that is gone. The next stage, remove stop words, bring it to lowercase, and finally throw it to a step. So that biggest string eventually comes down to this representation of what the numbers look, what the words look like uniquely in this. So the way we created the vocabulary is to use that entire set of data corpus, put it into the same process, what I did with one ticket, create a unique set, and we ended up with something in the range of 40,000 plus words in the dictionary. So remember, guys, we talked about our neural network where we said the input is a number, right? So we need to have some representation of converting a document into a number. That process is called vectorization. So we already know the first 2 steps, the text cleanup and everything, that part is sorted. The strategy which I first used for the vectorization was to calculate term frequency. Term frequency is defined as the number of instances a word exists in a document. It's as simple as that. It's just doing a frequency map of the document. So if you take a look at the entire vocabulary, and if my vocabulary is, let's say, 40,000 words, then every document can be converted into an array of size 40,000 with numbers over there, which represents 0 to x, whatever that number is, where it says that this is the frequency of this word existing in this document. So this is the vector representation of this document. Using the technique for the vectorization, and now we know what the positive and the negative inputs are, you basically do this pipeline thing, throw into vectorization, and then we end up training the multi-layer perceptron. You end up with a model, but well, every model is not good enough. What we wanted to do was to test out whether how good this model is performing. And our initial assessment on this model was an accuracy of something in the range of 63 to 71%. Why the difference? It depends on the architecture of the neural network, how many hidden layers you add, what algos you use. So we tried all sorts of combinations. There's a nice technique called grid search in sklearn. You can use that to actually do the comparison of multiple models and do that. So it makes it easier. But eventually, we ended up with 63, 65%. Was it good enough? Probably not, right? Like if your decision making is that inaccurate, you might as well do it manually because you don't trust it. So we tried, okay, let's do ensemble classifier. Well, the idea of ensemble classifier is very interesting. The ensemble classifier basically says that we will take a set of weak models which are not very accurate, make them vote, and a weighted average of that vote is the final decision. So even if we have a set of weak models, we end up with something which is an ensemble classifier, and this final classifier could be a much stronger model. So we did that. We did a different set of architectures and everything. We did a voting. We'll call it the model 1.5. We reached to accuracy of 78%. Was it good enough? Sure, good enough, but well, we could do better. Because with 78%, there's a good 22% chance that you're going to miss something, right? And if you remember, the problem statement I talked about was an incident. Incidents are probably less than 22%. So we want to make sure that the final quality of the work is better than that. So verdict, not good for use, right? Move on. So a little bit of a self-reflection, trying to think what went wrong in this model. The first thing which I felt was wrong is that when we're choosing the term frequency, we are not exactly capturing the semantics of the model, semantics of the language, which is presenting something. Just counting how many times a word exists doesn't necessarily represent the intent of the document, right? We need some way to understand that. And the second thing I wanted to call out was when I used the MLP, basically the multi-layer perceptron or the neural network the way it was, each word is represented differently, right? They don't necessarily have a correlation with each other. We need some way so that basically the words which are following each other have some meaning, right? Like a simple idea, proof of concept. If I take proof and of and concept separately, it doesn't really mean much. But you put them together, it has it has a specific meaning to it. So I wanted to bring these two things in mind, and then how do we solve this problem, right? So let's explore a little bit deeper. What options does machine learning offer us? So the first thing we wanted to explore was the unsupervised learning models. So unsupervised learning, there are a lot of good algos on that. You can do, k-nearest neighbor, you can do continuous bag of words, bunch of ideas. But at the end of the day, unsupervised learning are basically unlabeled data where you don't know really how you classify something, but you can try to form natural clusters. So you can say, hey, this word is closer to another word, and therefore they sort of mean similar, right? They're sort of related to each other. So you can actually form natural relationships between between words using unsupervised learning. Why this was important? Because when I'm reading a document usually contains a series of words which come adjacent to each other, or they mean something similar to each other. And that is what we are trying to extract out of the unsupervised learning technique. The second concept I wanted to touch was the convolutional neural network. This is a different kind of neural network. It's typically used in image processing a lot. So the idea of image processing, why it is used in image processing and why it's very, very useful is because it does not take every pixel by itself, right? Or every feature by itself. If you take every pixel of the image of the dog, it probably wouldn't mean much. But what it really means is which pixel is close to which one, and how are they forming edges, how are they forming the eyes and whatnot, right? And then eventually you'll be able to reach that, okay, yeah, what this really means. It's pretty useful in image classification. So I want to use that for understanding. If I can use the same technique to make sense of the sequence of words, because I don't want to treat the words as individual pixels, but the series of words, the sentences, as something which is more of a edges of the of the image I just showed you. So something like that. Okay. So final implementation. This one worked. We'll call it clairvoyant. I wanted to call it the Oracle. I like matrix, but somebody took Oracle already. So we're like, all right, let's stick with clairvoyant now. So we started there, and now this one works. So let's get into it. So we were using Spark as an example. So I wanted to keep the base as Spark, just speeds up the whole training process. And the corresponding library, which I wanted to use this time for NLP, is not NLTK. This one is Spark NLP. Does a very similar thing, goes faster because you can parallelize the stuff. So the standard steps, tokenizer, what tokenizer is, breaks out on white spaces. The next stage is lemmatizer. What this one does is that it brings down variants of the words to base word, right? Like a good example is there are different words like improved, improving, improvements. Those words essentially come down to the same base word which is improve, right? That's a good example of it. So from a classification perspective, you honestly don't care what variant of the word it is. You want to have the base word. The next thing is normalizing. Sometimes the words contain variants like small case, uppercase. There are different ways to write resume as a word, right? You could actually still bring it down to the same word. The idea is to come out as the minimum number of words required in our vectorization dictionary. And finally, the stop word removal. This one we already talked about. It's the same technique. So this is going to be our Spark NLP pipeline, the text processing pipeline, through which we'll clean up the text this time. And we go back to our original diagram. So we take all this stuff from different sources, put it into a raw corpus, put it to the Spark NLP pipeline, and this time, instead of just doing like a set classification of just an arbitrary number of words, we modified that technique and created a unsupervised clustering model out of it, which is essentially generating. So what it is actually doing, if you have to visualize this, like, okay, as humans, it's harder to visualize 300 dimensions, so we'll try and visualize them less. So if you think of this room, and if I was to take a word and throw it at a point in this room so that it is closer to the words associated to it, you will see this entire room full of words where, you know, there's a cluster of words over there, there, and so on, right? It's sort of like a clustering problem. The same thing I did in 300 dimensions. And as a result, we just test it out in the Apache Spark view. So if you find what words are closer to the word data frame, for those of you who has touched Spark, or for that matter, pandas, you know, the word data frame associates itself to data frames, data set, columns, pandas, whatnot, right? Those words are very, very close. What it is telling us is that the unsupervised learning technique we used to create these clusters is working pretty fine. And the right side you are seeing is essentially the vectorization. What does it mean? The best way to represent a point in a two-dimensional space is the coordinates of it. So just convert that into a 300-dimension thing. So in a 300-dimension space, if you were to visualize these words, the right side image is actually the coordinate of that word. So instead of using term frequency, this time I'm using the coordinates of that word as the numeric representation of those words to, you know, to what it will look like. Some of you, I'm sure you would have visualized this whole thing in 3D. Amazing. Thanks a lot for that. For the rest of us, let's take a look at this, right? So what I'm trying to do here is to basically compress 300 dimensions down to 2 dimensions. Obviously, it's not going to be exactly the same model, but this is what the word vector visualization looks like, right? So I just took 2 examples, like one was PySpark, one was data frame. We wanted to see the words, the blue words are the ones which are closest to it, the green ones are the next closest to it. Well, visually you see some of those are closer, but that's in 2 dimension, right? It's compressed, so let's not fall for it. So with this technique of vectorization, so this is our revised technique. The next stage, what we do is we go back to our training, right? In this training, it's the same process, except that the vectorization is not a term frequency. We use this 300-dimension vectors, and we need to have a training in a way that the input is a constant length. So what we did was that we picked up the first 1,000 unique words after processing. Why 1,000? Well, there's no reason for it. It's an arbitrary number. But I wanted to believe that if you cannot make a decision after reading 1,000 words, you probably cannot make a decision, right? So let's go with that idea. And we're going to use 1,000 words. So basically, my input to the convolutional neural network is like 1,000 words, each scaled up to 300 numbers of representation. So the input is like 300,000 values. That's what my input is for each document. And the output is 2. Why 2? Because I wanted to understand what is the percentage of confidence which says that this is required for review, or and what's the percentage not required. You could say it's like, hey, it's 100 minus the other one, but might as well test it out. So with this training, we went through the whole thing, and the final result was clairvoyant. Well, so this is the concept of a confusion matrix, which essentially is testing the final training data and trying to see what it looks like. So the rightmost side, you can see the support is actually saying how many instances were used. So a total of 700 documents were tested against this thing. And what we identified was that we got a pretty good accuracy there, right? That's 98% accuracy. That is something, okay, yeah. So that is something we can live with. With a 98% accuracy, this is something that we can deploy in our environment, and we can actually rely on it. You can always say there's 2% mistake, but if this was not 2% mistake, I would have said the model is really not working, so we don't have to worry about it. So with this confusion matrix, this is the final model, and obviously, once you have the model trained, what you do is, for any new document, any new feature, You can use this anywhere, right? Like anything which defines a natural language. So you can actually use it on your Jira tickets. You can use it on your Google Docs, PRD documents. You can use it on your PR comments, for that matter, right? When you do a GitHub check-in, right? Whatever you're putting there. It's all natural language. And as long as it represents something which is to deal with security, you can classify it. So it's the same process. Go through the threshold. And at the end of the day, why did we all start with this? Was because the number ratio between the security teams versus engineering was too high, right? That was the problem. So this thing is going to give us a confidence score of how critical this issue is. And at the same time, I can put a threshold saying that, hey, hold on, my team can only handle up to, let's say, 90% of confidence score. So we are going to prioritize only those many. And so on, right? So you can actually play with what you want to prioritize on. Tomorrow you get like 20 more people in your team. Sure, bring down the score. Why not? So what you're going to do is, I recorded this demo. I wanted to record this for two reasons, obviously. I'm in Black Hat, a lot of smart people here trying to, I don't want to put my machine on the network and then mess it up. And the second thing is, this demo, we all have been there. It always messes up. So let's hope it does. So I needed to record this one. Hopefully the video will work. So I'm going to run through the video. This is the Apache Software Foundation Jira. You can actually see what I'm doing here is I'm extracting the list of new features which were created since 2018. So I download that as a CSV file. And this is where I'm basically going to introduce this CSV file as my input, do a reclassification, and see how this works out. Okay? And while I was downloading this, we tried with all new features. That was like 2,200 plus features. And without creating an account with a public account, there was only so much that I could download. There was a limit of 1,000. So I had to restrict it the last 5 years, whatever. So over here, as you can see in the code, what I am doing is that all I have done is that I have started using that other file as my input for the classifier. And there you go. That's the magic trick, right? So once you run this out, this takes a little bit of time. I have kind of cut down the time on the video, but this approximately takes 40 seconds to analyze something in the range of 800 plus issues. Over here, you can see it's downloading some stuff, which is why you need the internet. So if I try to do this live here, I was afraid somebody's going to hack my machine and I will not be able to work on it, so why not? At the end of the day, this classifier works through, and you essentially get a list of issues with a confidence rating. So as you can see there, on the left-hand side, that's a confidence score, which shows what percentage of confidence it is that something requires a security review. What I'm going to do is, there was one good way to do is like, hey, why not just push everything, right? Like, so we want to see how bad or how good is the result in terms of stats. Well, I'm more of a VI guy, so we'll just do a quick word count. What I see here is this is approximately 119 issues which were required out of 800 some issues. So it's not a bad ratio if you think about it, right? And that's pretty much very super realistic. This is approximately like what, 12 to 13%. So that's one part of it. But at the same time, what kind of issues were marked for security review, right? You want to understand wherever there are security improvements or anything that has a security impact, right? So those are some of the examples. Let's run through the results in a different way. So I picked up some part of the result, push it here. And you can see the content out here. And most of us have been in security, right? And you can see the results make sense, right? So parameterization of SQL, support plain text authentication in Kubernetes with Spark, OAuth dependency check. Literally a lot of things that would typically have a security impact gets recorded. Usually, prior to this, as we were doing things, a developer would have to wait forever to get a response that, hey, security team, can I proceed with this without a security review? And we have a huge backlog. We can't just say, oh yeah, go for it. But now with this, we can automatically put a comment on Jira saying, hey, this is low risk. We don't care about it. Move on, right? So we speed up engineering. We speed up security. It's all good. Moving towards the end, some super high-level key takeaways. The first thing I want to call out is this is the time, essentially, that we move to the next stage of automation, right? What we started in the beginning. It's not just about repeatable and process-oriented, but a lot of things which could be done with a little bit of intelligence and domain knowledge can be automated, right? Which is great. The second thing, spoken English, engineering English, not the same thing, okay? CNN could be a news channel or could be a convolutional network, right? So that's just another example. And again, I'm not endorsing for or against CNN. I have no affiliations, so please, let's keep it away. And the last thing, AI can nitro boost our SDLC processes, DevSecOps. I think this is a time when you will actually see new domain, kind of a lot of new books coming up in this area, which will essentially talk about AI-powered DevSecOps, right? There are a lot of things you can do here. Well, now is the time to explore that. Before I end, I would definitely like to thank Lydia. She went through a bunch of rehearsals with me in the coaching program. Thank you so much. I don't know if you're here, but thanks a lot. At this point, I would open for questions. There are mics out here on each row. If there's any question, please walk up, and I'll try and answer the best I can. Thank you.
Hi. Do you have plans to do the same for, let's say, data governance issues, to detect it for that?
The basic code around understanding the language is still going to be a constant. How you classify is what your choice was. So like within Databricks, we did another set of classification after this, where we are even rating it for high, medium, and low. Tomorrow you can use a privacy detection, you can do legal detection, you can do the data governance thing. Hey, does this impact FedRAMP or not, right? Whatever you train on, as long as you understand the language, you should be good. So I've tried it on 2 or 3 use cases, it works great.
Okay.
Hi, thank you for the presentation. Did you validate whether the model did not miss some important part? You have shown that, okay, obvious ones there are, but
right.
I would guess that normal people would, reviewer would get the normal ones, but the one which would be missed.
Yeah. So that's a great question. This is actually why we always try to optimize on the F1 score on the chart, right? So the F1 score basically talks about the true false positives and false negatives as well, right? A high F1 score usually says that you are actually good on false positives, false negatives as well. And that range is like, at least for the required ones, we missed like 2%. On the non-required, you missed like 1%. So not so bad, actually.
Thank you.
Thank you.
It's regarding the vectorization of the words. Did you look into other methods? And also, why did you choose that one?
So this technique is, okay, the reason I chose it is because there are standard word vectors available for normal spoken English, which you can just download on the internet, right? Those are pretty much well-tested methods. I think the Glove 6 billion or something. It actually trains on the entire Wikipedia and Google and whatnot. So I assume this was pretty well tested, so why not? Let's use the same technique, create something similar, but for the engineering and security domain. So that's the reason. Thank you.
Hi. You know when you showed unsupervised learning and you had the clustering diagram?
Yes.
I was just wondering, was the absence of good quality data from some of your sources, did that become an indicator that led to any action by the security team?
So the absence of good quality data was something we felt a lot when we were trying to classify in the severity of the problem. So high, medium, and low, because that's something which there is always a lot of subjectivity associated to it, whether this is a critical issue or not. Over here, we almost used something like 6,000 documents on each side to test it out. And again, the idea was never to actually pick up a positive or a negative example, but to pick up what language, what natural language is used to talk about those areas. So it worked out pretty well, actually. Thank you.
Hello, MJ.
Hi.
Thank you. Very interesting presentation. I have 3 questions. The first one, how much time did you spend to get clairvoyant? This is the first one. Second one, you talked about the anticipation. I didn't think that you have presented the next step about the presentation. And the third one was did you scratch the surface about the frequency of words based on the languages? Because if we have Jira with multiple languages, it can be another cumbersome.
That's true. The current training is primarily on English. We could always use that, build a different vocabulary, or maybe even combine vocabularies, because nothing in the code except for using the stop words is language specific. So you can always do that, bring in multiple languages, use different stop words, you can play with that. But other than that, none of the code is to do anything to do with specific language. So that is still doable. How much time did I spend? I would say approximately I think a couple of months on this. But yeah, there's a funny story around it, but some other day. Today's not the day. And sorry, I missed the second question.
The anticipation part.
Could you please elaborate on that question? I mean, there's a significant anticipation on whether you will get it or not. But
you presented on one of your slides the way that you can eventually forecast
yes,
the number of
yes,
tickets that would be treated in advance.
Correct. So yeah, that was, I think, this one, right? Something like this, right? So yeah, I mean, obviously there is a significant amount of anticipation in that, but eventually the quality is something which if you just train on only Jira or only one area, the quality is much, much worse. You have to start playing with a lot more sources. Like over here for this source, I played with PRD documents, with Jira tickets, with, public documentations of Spark and all the associated things with Spark NLP and PySpark and whatnot. Anything which is related, anything you can find in that area. And that sort of improves it. Am I saying you will never miss something? No, there was a 2% error. So I'm not saying that you'll never miss something. But is it better than just relying on a developer to make a judgment call and you trusting it? Sure, it's better.
Thank you.
Thank you. All right. Well, thanks a lot, guys. Thank you so much. Thanks for coming here.